Okay, so I'm coming back to this topic. It was just on the back burner for a while about uh, relativistic forces when mass is above a certain uh, state or scale, and dark matter. So I wanted to go through one by one and just see. So I started watching something and I had some comments, so I decided let's just do it like this. No conflict between general relativity and quantum
Physical
mechanics.
reality at its heart is the four fundamental forces: gravity, electromagnetism, and the weak and strong nuclear forces. The so-called conflict between general relativity and quantum mechanics has two reasons. The first is because relativistic effects don't correlate to observed atomic phenomenon. Relativity is fundamentally about the gravitational force. Gravity is astronomically weak compared to the other fundamental forces. It is the domain of large objects like planets, stars, and galaxies.
Okay,
The weak nuclear force is 10 to the 25th power times stronger than gravity.
right.
Electromagnetism is much stronger than the weak nuclear force, and the strong nuclear force is even stronger.
Right.
Gravity is far too astronomically weak to have any effect on atomic phenomenon. The
Okay.
term quantum gravity has virtually no basis in physical reality. Atomic phenomenon is the domain of electromagnetism.
Well, except that um, using quantum gravity, LIGO actually measured a gravitational wave. So,
The weak nuclear force and the strong nuclear force. The second reason is about singularities. Singularities are a mathematical construct only and do not exist in physical reality.
yes, I would say singularities are a mathematical construct that lets you know that you're that you have reached the limits of your current mathematical model or your current physical model, and there's some physics going on beyond your current understanding.
Einstein is known to have repeatedly spoken about this. In the 1939 journal Annals of Mathematics, he wrote, "The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities." Schwarzschild was the first to raise the issue of general relativity predicting singularities, do not exist in physical reality. Although the theory given here treats only clusters, star clusters, whose particles move along circular paths, it does seem to be subject to reasonable doubt that more general cases will have analogous results. The Schwarzschild singularities do not appear for the reason that matter cannot be concentrated arbitrarily, and this is due to the fact that otherwise the constituting particles would reach the velocity of light. Singularities have always been a stubbornly persistent fictional term. Attempts to unify general relativity with quantum mechanics is attempts to unify the ununifiable.
With 19 hotel brands.
I don't know, never say never. So, oh, that was it. Okay. Okay, let's move on to the next one. So,
If a ship travels at a constant
just commenting on the previous one, what do I think of that one? It's a general statement. It didn't propose any alternative. It just says that the author does not believe in singularities.
1g acceleration rate, it would get to Alpha Centauri, our nearest stellar neighbor, in about 3.6 years.
Yes.
7.3 years would pass on Earth. Some sources have the trip times as high.
Um, hmm. Uh,
High as 7.7 ship years or 12 Earth years. This includes turning the ship around halfway to decelerate. It would achieve about 0.95% light speed after about 1 year. A 10-ton ship would require 10 tons of continuous thrust. This is by far the fastest way we can get to other worlds, and the ship would have gravity the whole way. All that is needed for this is a true fission rocket that can put out thrust for long periods. A true fission rocket should consume uranium or plutonium only. They are both jittery atoms that are on the verge of fissioning all by themselves. There should be a way to get them to fission in a linear fashion. What's needed is a controlled, time-released nuclear explosion. In an atomic bomb, fission occurs when neutrons hit uranium or plutonium nuclei. This is because they will not tolerate an increase in mass. Due to the equivalence of mass and energy, the same should be true if you infuse them with energy.
What?
Uranium and plutonium are metals that conduct electricity. If two charged copper cables come together, there is a flash of light and heat is released. What would happen if the cables were made from high-grade uranium? Would it be the same amount of energy released, or more? If the answer is more, then this simple process, it could be the basis for a true fission rocket. Simply put, they would consist of a mechanism to send positively charged atoms towards negatively charged atoms. These would be low output compared to conventional rockets, and for use in the vacuum of space. They would have to be made from a non-conductive ceramic material. Another potential method would be to have two electrodes with a narrow specific gap and a specific electrical current set just below the threshold of causing an electrical arc in a vacuum, precisely so it only requires a single atom to cause the arc to occur. The idea being to pop uranium or plutonium atoms like fuses. Another potential method would be to use laser or electromagnetic forces. What would happen if a powerful laser hit uranium or plutonium atoms?
What? Okay. It's very funky music.
This graph shows the phenomenon of dilation. It illustrates the phenomenon behind the phrase, mass becomes infinite at the speed of light.
Like, it's an arguable phrase, so what we do know is that momentum becomes infinite at the speed of light. We know that because of the gamma term. Again, watching other videos and just recalling what little I remember from my GR courses, it's a nice and convenient trick to subsume the gamma term into rest mass and call it relativistic mass, because there's one less term floating around. But does it have a real physical consequence? Can you say that the mass itself is becoming larger? That, I don't know, there's a big debate around that.
When the ship reaches about 75% light speed, there would be a degradation in communication, because as the graph shows, relativistic effects would become noticeable at that point.
Okay.
When the ship reaches 95% light speed, communication will be virtually impossible. From an Earthbound observer's point of view, the ship's existence would be smeared through space-time.
I don't know. I mean, if you are, like, I am assuming that there's a theory that is beyond relativity, that is beyond quantum physics, that there's a paradigm shift that still is hopefully on the horizon, and I live to see it. But if you're working on the premise that that doesn't exist, then we can explain a lot given the current understanding of relativity. Firstly, you need to distinguish general relativity from special relativity, and within either relativities, but specifically special relativity, the speed of light is always constant. So I don't understand why communication would become an issue, because you send a message and it will still take the same amount of years to reach.
From the ship's point of view, everything would be normal. Relativistic effects are all from the outside observers.
So this is kind of a little bit not correct because in special relativity, and you're just saying, you know, like just thinking about this with special relativity alone, I can say you're kind of hitting problems right now because, okay, to accelerate to get to 95%, you're dealing with general relativity, you're dealing with, time dilation, things like that. But let's say you accelerate to 95% and you stay there, right? So your thesis is that, okay, once you've accelerated and this blob is going at 95% the speed of light, it's like spread out, the mass is spread out, but within the ship everything looks the same. But in special relativity, the whole starting thesis is that every frame of reference is equivalent, and so being equivalent. So, for example, if there are two spaceships, one is traveling fast, like 95% the speed of light, it would observe the other spaceship to be shorter than the spaceship would measure itself within its own frame of reference. So that's called length contraction. And so over here, it's a little bit strange because what he's saying is the opposite of length contraction, that it's going really fast, but instead of seeing the length contracted, it's spread out everywhere, which I don't understand. But even beyond that, like, just take your acceleration out of the equation. You've accelerated, now it's steadily going at 95% the speed of light. Once you step into the frame of reference of your spaceship, you should see the equivalency. It should be equivalent to the universe going at 95% the speed of light. So the universe should now exhibit the same sort of spread out and not being able to see it. So effectively, according to your own logic, if a spaceship goes at 95% the speed of light, the universe, everything should just disappear. All galaxies should just disappear.
Point of view.
Or get blurry or blurred out.
Due to relativistic effects, the ship will only have a weak interaction with regular mass during the high-velocity portion of the trip. It would be at maximum velocity in the voids between star systems, where the chances of significant mass being in the flight path would be astronomically low. It would also need a powerful radar, RF.
I'm not sure where that prediction comes from. That it like what he said right here. Due to relativistic effects, the ship will only have a weak interaction with regular mass during the high velocity portion of the trip, which I don't. I mean, if you're in the high velocity portion of the trip, it's so you are saying that the rest of the universe is blurred, has mass. You perceive the rest of the universe as having mass dilation, because if not, if it looks the same, then you should interact with it the same. So there's kind of a dichotomy over here. So, like, you can't have it both ways. You can't say that the equations are correct as is, but then not have a symmetry in the frame of reference. And so I'm a little. I don't think this point has been thought through very rigorously.
Velocity in the voids between star systems, where the chances of significant mass being in the flight path would be astronomically low. It would also need a powerful radar, RF emissions will travel at light speed regardless of the ship's velocity.
Right.
Interstellar radiation is not a problem either. A couple feet of asteroid dirt and/or graphite surrounding the ship will keep it out. With the constant 1G acceleration method, a ship can span the entire diameter of our galaxy in 24 ship years, or 113,000 Earth years.
So you can span the entire diameter of the galaxy in that years, assuming that you're only accelerating, but so the closer you are to a gravitational field or an acceleration, the higher acceleration that you experience, the faster that the faster time appears to go for you. So that's where that film is kind of helpful, because it's really easy to confuse what happens where. The film called oh my god, I can't remember the name of the film, with Interstellar. So when they go into an extremely large planet close to a supermassive black hole, they're experiencing higher gravity, which means that time goes, it's going, so they experience fewer years than the guy who's out of the so it gets kind of confusing, but like even if I just skip over this bit,
Systems with stars.
like I do know that the twin paradox, if you got twins, one travels to a distant galaxy and comes back. Is the older the same? And considering, and if you say that the twin on Earth sends a message every year, then it would appear that, like, how can one twin send more messages than the other one receive? But when you do the calculations, you kind of find that in the period of acceleration and deceleration, time is different. And so when they meet up again, the number of messages sent is equal to the number of messages received, which I'm not sure is relevant here. I'm just sort of thinking out loud.
Similar to our sun, can be reached in under 10 ship years.
The amateur.
I'm not really sure. This one is no dark energy, and then this one. So let's just. And then this is different. This is dark energy, not dark matter.
There is only one reason to postulate dark energy: to explain the exponential expansion rate of the universe.
Right. So dark energy essentially is a fudge factor that is injected into our current known equations, because the universe is expanding at a rate greater than what we currently measure, given the observable mass or observable energy. And so we have to inject that there's some like extra energy out there in vacuum, which is maybe not vacuum fluctuations, maybe beyond vacuum fluctuations. It's a bit, fuzzy. I'm not completely on top of the field.
The expansion was discovered in 1929, and the exponential aspect was discovered in 1998. This is when the concept of dark energy began to become mainstream.
Mm-hmm.
To date, all studies to discover dark energy have been
So the term dark energy, at least from my point of view, is not a statement by the scientific community saying that there is dark energy out there and we need to find it. It is a statement by scientists to themselves, and they kind of ignore the rest of the population because everyone gets confused. It's just a statement. It's like a placeholder to themselves, saying like, "Oh, the current equations only hold if there's this magical, science fiction dark energy, which we don't see." So, like, hey, dark energy. Is there a new model? Is there a new paradigm? It could be anything.
Fruitless. Electricity is drawn towards potential, and the universe as a whole behaves the same way. Electricity comes into our homes because the neutral circuit provides the potential.
So essentially, it's like water. You go from high potential to low potential. So, yeah.
Lightning is drawn towards grounding rods for the same reason. If something accelerates at a constant rate, it will get faster and faster.
Right.
The exponential expansion rate of the universe is what the known laws of physics would predict, provided gravitational forces are not strong enough to counteract the process.
The exponential expansion rate of the universe. So the current expansion rate, which is exponential, of the universe is what the known laws of physics would predict, provided that gravitational forces are not strong enough to counteract the process. So if there's no gravitational processes, again, there is like a lack of equations over here. So, it would be nice if there's an equation and a demonstration and this number, not that number. Because right now there's a lot of just, taking the video on faith.
The universe expands and galaxies are along for the ride.
What?
Physicists in the last century did not postulate dark energy because they understood that the expansion was a fundamental property of the universe. The fact that the expansion is accelerating does not invalidate their reasoning. All studies to discover dark energy have been and will be a waste of resources.
Oh, what? No. I mean, it's a big flaw in our current models. So we need to address and explore the flaw. Oh, okay, that's okay. So this guy really doesn't like dark energy. Singularity is a stubbornly persistent fictional term.
Most people don't know that Einstein said that singularities are not possible. In the 1939 journal, Annals of Mathematics, he wrote, "The essential result of this investigation is a clear understanding as to why the Schwarzschild..."
Is it annals or annals?
Singularities. Schwarzschild was the first to raise the issue of general relativity predicting singularities do not exist in physical reality. Although the theory given here treats only clusters whose particles move along circular paths, it does seem to be subject to reasonable doubt that more general cases will have analogous results. The Schwarzschild singularities do not appear for the reason that matter cannot be concentrated arbitrarily. And this is due to the fact that otherwise the constituting particles would reach the velocity of light.
What?
He was referring to the phenomenon of dilation, sometimes called gamma or Y, mass that is dilated is smeared through space-time relative to an outside observer. The graph illustrates the
Is smeared through space-time relative to an outside observer. The graph illustrates the phenomenon behind the phrase mass becomes infinite. No, momentum becomes infinite. You can say that. I mean, again, I went through this in 2 videos ago.
The phenomenon behind the phrase mass becomes infinite at the speed of light. The best way to understand this is to imagine a ship leaving the Earth at a constant acceleration rate.
Okay.
When the ship reaches 50% light speed, as viewed from the Earth with a magically powerful telescope, it would appear normal because, as the graph shows, nothing has changed at that point.
Okay.
When the ship reaches 75% light speed, the image would have to be a little fuzzy, because as the graph shows, relativistic effects would be noticeable at this point.
Okay, so I don't know why it would need to be fuzzy. So it's a...
When the ship reaches 99% light speed, it would not be visible because, as the graph shows, there would be virtually no relevance at this point. From an earthbound observer's point of view, every aspect of the ship's existence would be smeared through space-time. From the ship's point of view, everything would be normal. Relativistic effects are all from an outside observer's point of view.
So according to the ship, if you're in the ship, the rest of the universe looks blurry then, or...
Wherever you have an astronomical quantity of mass, dilation will occur because high mass means high momentum. There is no place in the universe where mass is more concentrated than at the center of a galaxy.
dilation because high mass means high momentum. No? No. Momentum is mass times velocity, or relativistic terms times the gamma factor. So if you go very low or zero velocity, then you don't have high momentum. But also it's velocity, it's momentum relative to a frame of reference. So there'll always be a frame of reference in which you have very high momentum.
Galaxy. Einstein wrote about dilation occurring in regions that would have less mass than that which would exist at the center of common spiral galaxies. Since high mass means high momentum, it's safe to say that according to Einstein's math, the mass at the center of our own galaxy must be dilated. This means that there is no valid XYZ coordinate we can attribute to it. You can't point your finger at something that is smeared through space-time. Or more precisely, everywhere you point is equally valid. This is the explanation for the greatest mystery in science, the abnormally high rotation rates of stars in spiral galaxies.
Well, it's one of the greatest mysteries. It's not the greatest mystery.
The reason for the theory of dark matter. The missing mass is dilated mass. According to Einstein's math, galaxies with very, very low mass would not contain dilated mass because they do not have enough mass at the center to achieve relativistic velocities. To date, 5 very low mass galaxies have been confirmed to have normal star rotation rate.
I mean, if according to your own theory, you can have, like, any mass can be relativistic then. Because there'll always be some frame of reference, or many frames of reference in the universe, which will perceive that mass as going close to the speed of light. But it doesn't exhibit dilation. So, like, this is not really a theory even, it's just a collection of ideas. In order for this to be a theory, you need to put down the math and, like, be a bit more rigorous. So, I mean, like, this just dilation speed of light, this is just a logarithmic graph. It doesn't really, I mean, essentially you just got an exponential curve here. it doesn't say anything. There's no like this is a bit of a this is a bit of a non-information graph. The closer you get to the speed of light, the more dilation is observed, and what dilation. So it's sort of conflating a number of different things. And
rates. In other words, they showed no signs of dark matter. This is virtual proof that dilation is the governing phenomenon in galactic centers. There can be no other realistic explanation for this fact.
No, there can be a lot of realistic explanations. I mean, if observables meet with your expectations in some scenarios, but not in others, it doesn't really mean that much. But I mean, this whole concept of mass dilation I don't see how it helps anything. Like, how is it helping? Like, you're not explaining your position very well, which, so I watch your other videos now, and they've kind of taken away from your initial argument, because it sort of feels like you've confused the two regimes of general relativity and special relativity. And when mass is large enough to overcome the strong nuclear forces, you do observe supernovae. So there are supernovae that have been seen, and depending on the initial mass of the sun, when it collapses, they're able to confirm that it either collapses to a brown dwarf or a pulsar, or into a black hole, so a singularity. And again, just getting back on point, singularity is a way in which scientists or physicists communicate to each other that there's some unknown physics in there. We've reached the end of our known models, but it doesn't mean that the known models are completely wrong. So it collapsed an infinite amount, and we've observed black holes. And so it's a bit, I don't quite get it, like, because he's not talking about density over here, that if density gets to a certain point, you observe something. He's talking about, like, just total mass. If the total mass is a certain amount, irrespective of density, then you exhibit relativistic effects, and it's kind of like, well, I mean, density also plays a role. So I'm trying to come up with a good argument, or a way of conveying it in a way that's simpler, but I mean, right now, that's the best that I could do. Is we do have evidence for supernova, we have evidence for pulsars, we've detected black holes and curvature around black holes and lensing effects. And so our current mathematical models are very, very accurate. It's just when we look in the center of our galaxies, given our models, the galaxy seems to rotate faster than our current estimates of mass. And like how mass dilation can explain, like, again, it's a bit difficult going through this. I would not, if this is a paper, I would definitely not publish it, definitely not recommend it for publication, because the statements have not been clearly made. So if you were to make a clear statement, like state your position exactly, which is, it is our belief that there is mass dilation, and in the case of mass dilation, give a fair, bulletproof argument for why you wouldn't observe the mass. There'd be a lot of mass that's not observable because of it being fuzzy or whatever, which again, I've spoken about how the example given is not very convincing. But even if I were to accept that point and move on, you then need to state clearly that because it's fuzzy, that means that the actual mass at the center of our galaxies is much higher than what we currently can observe. And with that higher mass, then that's the dark mass. The dark matter is explains the rotation of the the higher rotation velocity of the galaxies. But I mean, in its current form, it just there's absolutely no evidence that when something moves fast, it becomes fuzzy. And so just because there's a handful of low density galaxies that do not exhibit the dark matter phenomenon doesn't mean that your theory is correct, because you haven't explained anything. It just an extra data point that indicates that where you do have high mass, something else is going on. And then with respect to dark energy, again, there's no mathematics provided. It's given our current models, given with what we currently measure, the acceleration, the fact that the universe is expanding at an accelerated rate, right? In the last century, it was the universe is, it's expanding because the Big Bang, blah, blah, blah. Will it go on forever? Will it reach a stasis point? Will it reach some maximum and then come back and contract with, never-ending Big Bangs? These were questions. And then when they found out that, oh my God, they measured and it appears, according to our measurements, that the universe is expanding at an accelerated rate, right? That did not make sense with just the Big Bang theory. So in order for the galaxy itself to be expanding at an accelerated rate, that means that energy is being poured into the universe. The universe is expanding at an accelerated rate. It means that there's extra energy being poured into the universe all the time, and that's what they call the dark energy. Again, it's this fudge factor that they put in, just like with Max Planck and quantization. Put it in, now the theory matches what we observe. What does this mean, right? And so the physical intuition between where this dark energy is coming from, why the universe is doing what it does, is not addressed at all in these videos, I'm sorry to say. It's essentially just a number of videos where the guy it doesn't explain anything at all, at least to me. And so it has not been that helpful. Sorry.